Hi everyone, my name is Ming, and I'm presenting with me today is Abhishek. We will be presenting on our MSR submission, a machine learning approach for vulnerability curation. So the first thing on the agenda will be to set a context of vulnerability curation and to describe some challenges along with it. Next, we'll dwell on the machine learning approach and the journey we've taken so far, before moving on to the discussion of our experimental results, and finally touching on the potential of improvement. So the software vulnerability issue is a constant issue where developers have to deal with. This issue is not going to be simpler, as software applications often depend on multiple levels of open source libraries. Keeping track of vulnerabilities in the first party code is already an issue. And so it is almost impossible to individually track all vulnerabilities in third party code. So in this talk, when we mention about vulnerability curation, we really mean those that are found in third-party open source libraries used by software applications. To help speed up our insights of vulnerabilities in third-party libraries, we process data from various internet sources, from tracking the National Vulnerability Database for CVEs to developer-oriented sources such as Jira, Bugzilla, GitHub, Git mailing list, and as well as the relevant vendor release notes. So curation from all those sources do help in our insights, but here's the problem. The final vulnerability curation is largely mainly a manual process, as researchers have to verify each source individually. And across different programming languages, we also currently support over 2.6 million open source libraries and are actively tracking more than 50,000 Git repositories. The challenge of creating vulnerabilities become harder as number of sources grow, while keeping the same number of security researchers. So what we really needed was a solution to scale the system, and our direction was to move to a machine learning approach. In our first iteration of machine learning approach, published in the FSE 2017 by Chen and Asankhaya, we have gotten good results from syncing and training 20,000 Git repositories with over 3 months worth of data, as well as developer bug reports from over 5,000 projects created between 2012 and 2017. In that model, we achieved 0.83 precision and 0.74 recall. However, in that approach, we were dealing with a dataset which has a high imbalance ratio per source. For a certain source, items which were labeled vulnerabilities went as low as 5.88%. And further, we also wanted to expand the number of sources in our curation process. We have added more repositories and languages, and to increase our library coverage while having the same human researcher constraint. We have also noted that the newly labeled data, which were labeled vulnerable, has become a subset of the predicted positive dataset. So we needed a solution to balance and scale the system. Hence, we worked on this new machine learning approach that will automatically generate improved and evaluated models, which would be resilient to changes in our curation requirements, such as to support adding more data sources or adding a new programming language support. Over time, we also find that our data has become more imbalanced to as low as 3.29% are labeled a vulnerability. This will be an issue for the performance of our future machine learning models. And to deal with this situation, we have thought of implementing new features in our machine learning routine. So now I'd like to pass my time to Abhishek, who will continue on with the topic.
Thanks, Ming. I'm Abhishek, and hi everyone. I'm Abhishek, and I will be taking you through the next set of slides. So, as Ming already talked, we have a lot of data. A lot of it is imbalanced, but we don't have a lot of people, or we can't just scale the number of human security researchers. We have to label this unlabeled data. So To solve this, we looked at modifying our machine learning approach based on a machine method in machine learning literature known as cell training, which was proposed by Nigam et al. This helps us to utilize our unlabeled data. Uh, the unlabeled data we have is in two forms. One is that actually passes through our production machine learning pipelines, but is predicted as non-vulnerable. So it is something that the researchers never see because it is flagged as not a security issue. But in the next iterations of our machine learning training, we were not able to utilize it. Second set of unlabeled data we have is if you actually read the paper, we also, because we collect a lot of data, a lot of it we filter out through regular expressions. So that we were never actually passing through the machine learning pipeline, but we had the intuition that it will contain some informative data. So that's also what we wanted to use. And based on some academic research that we did, self-training is something that we found to be most useful for our case. How does self-training work? So originally, in the work presented in FSC 2017 by Zhao et al., we just had one machine learning model in prediction, which will give you a prediction score for a data item. And if it is greater than a threshold, the data would be predicted as a vulnerability. In our new approach for self-training, we have added two more thresholds, and the constraint is one is called high threshold and one is called a low threshold. And the high threshold should be greater than the production threshold that we're using, and the low threshold should be lower than the production threshold we're using. How do we use it? Is basically we run the data items that we want, the unlabeled data items through our production machine learning pipelines. And if anything is higher than the TH, that is the higher threshold, we kind of use it in the next iteration as a positive labeled data or something that should be a security issue or a vulnerability. And whatever has a prediction score lower than the lower threshold, that is TL, we use it as a negative label data. So just to give you an example, let's say these are the values for TH and TL. And we, as I already told you, we have two types of data. One was which actually went through the production machine learning pipeline, what was predicted as non-vulnerable. And the second was what failed at the regular expression filtering stage. What we do is we take all that data and again pass through the machine learning model, which is used in production, and we get these scores. How we can use these is just based on the thresholds, we can extract some data. So if you see the numbers that I highlighted in red, these are the data points which had a score less than TL. So in the next iteration of machine learning, we will use these as negative data instances. And there are two numbers that you see as green. So these actually came up from data which we were just throwing away earlier. But now we can see that because these are being predicted as positive, we can use them as probably, because the machine learning is predicting them as a security issue. In the next training iteration, we can consider these as positive instances. So this helped us to generate some machine labeled data without actually scaling this. Our security researchers teams are adding more human labelers to verify the issues. Does it work? Let's see. So the metrics that we use to compare the new models and the previous models. So the previous models is the one proposed in FSC 2017. It was only trained on the human labeled data, and the new one is the one which is trained on self-trained plus human labeled data. So we use the metrics of precision and recall. These are standard metrics. I would not go into deep details of these. The idea is to plot a precision recall curve and maximize the area under that. The model which is able to maximize the area is supposed to perform the best. Same as the higher the curve, the better the performance. The models that we use the features we used were word-to-vec vectors, which only currently use the text data present in the data that we crawl through Bugzilla or GitHub. And the machine learning setting is same. It's still a stacking ensemble trained on these features. Apart from the standard metrics of precision recall, we also created our own metric, which we call as deployment stability. So it is why we did it is because sometimes when we used to deploy new models, security researchers were not happy. Why? Because whatever the security the researchers had labeled as a vulnerability or a security issue, a new model would start predicting it as a non-security issue or predicting it as non-vulnerable. And sometimes when we deployed models, it used to happen for a lot of data which had already been vetted by the security researchers. So this is something kind of a unique issue we could only find when we were actually making deployments in production. So that's why we came up with this metric. What this metric does, it tries to evaluate the new model's performance on the data that has already been labeled and compares it to the production deployed model also. So it helps us to see whether a new model that we want to deploy, is it actually drifting a lot from the previous models and the previous data that security researchers have already labeled. So based on these metrics, if we only see the precision recall metrics, the new approach, the self-training approach, models trained based on that tend to perform better than the previous approach where we only trained on the human level data. We have the precision recall curve, the AUC, that is area under curve, increases for most of the cases. For data sources such as Bugzilla emails and reserved CVs, the improvement is negligible as they already had very high PRA AUC values. So yeah, for that case, we were not able to get a very high increase. But still overall, all the new models based on self-training tend to perform better than the previous models, even by a small amount. Based on the deployment stability, most of the times, whenever we train a new model, they tend to have a stability score of 0.9, which is considered good. That means that it agrees with the previous model or the model which is already running in production. Some cases, like for reserved series, if you see, once we achieved a score of 0.73. So in that case, even if precision recall curve for the new model is better, but deployment stability is low, we decided not to deploy the new models. So this metric kind of helps us to sometimes decide whether should we actually go ahead with the new model, especially if the performance improvement on precision recall score is not that high. There are some limitations to our approach. Currently, it's only limited to textual data. The data that we collect has a lot of code also, and that is something that we want to really utilize to improve our accuracy scores further. Data imbalance is still a problem because most of the data is still related. It's not a security issue. It's classified as non-vulnerability. So we are trying to see if somehow we can still uh, get better performance despite the data imbalance being a constant issue. Also, sometimes labels change. Data that was previously labeled as security issue, sometimes vulnerables after a certain point of time because there have been some changes in the libraries, they will change the label to negative. So how to handle such kinds of scenarios is still we are something trying to decide on. So overall, to give a summary of what we did in this work is uh, using self-learning helped us to utilize a lot of unlabeled data we have, and without actually increasing the human cost. Results do show that it works well as compared to only using the labeled data. It can be used as a technique to get more data for any machine learning systems that might be running in production for other industry or another firms. A practical issue of the models being very different from how they were behaving earlier is something we have tried to solve using deployment stability metric. It does help us to decide if we should not be deploying a new model, although the precision recall scores might be slightly better. In future, we want to deal with the problem of changing the labels, which I kind of touched upon earlier, and also to utilize the code features because we already have this data. So we are pretty sure that if we are able to combine this with the text features used, it would be helpful for us to improve the performance. Thanks for your time.